February 23, 1944, 23,000 feet above Gotha, Germany. Lieutenant William Lawley's B-17, call sign Cabin in the Sky, was coming apart in ways that Boeing engineers would have sworn was impossible. The number 2 engine wasn't just dead, it was gone, ripped completely off the wing by a direct hit from an 88mm flak shell. The number 3 engine blazed like a torch, flames streaming back 50 feet despite Lawley's attempts to feather the prop and activate the fire suppression system. But those were just the obvious problems. What the Luftwaffe pilots circling like wolves couldn't see from outside was the real damage. 217 separate 20mm cannon holes peppered the fuselage. The main wing spar, the structural backbone that held 30 tons of bomber together, had been severed in 2 places. The control cables for the rudder and elevators were hanging by individual wire strands, any one of which could snap at any moment and send the fortress into an unrecoverable spin. The oxygen system was gone, forcing the crew to share portable bottles at an altitude where unconsciousness came in seconds without supplemental air. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. And the co-pilot, Lieutenant Paul Murphy, lay slumped in his seat with most of his skull missing from a 20mm round that had punched through the cockpit glass. By every calculation the Luftwaffe had made about bomber vulnerability, by every structural analysis German engineers had conducted on captured B-17s, by every tactical doctrine that governed fighter attacks on heavy bombers, Cabin in the Sky should have been a burning crater in a German field. Instead, Lawley held that dying bird level with his feet jammed against the rudder pedals and both hands pulling the control yoke back into his stomach with such force that he tore muscles in his shoulders. For the next 2 hours and 40 minutes, he would fly 500 miles back to England, in an aircraft that German fighter pilots kept attacking because they couldn't believe it was still flying. See, the Luftwaffe had done the math on the B-17. They knew exactly how much damage these bombers could take because they'd been shooting them down since 1943. Their own tests at Rechlin using captured fortresses had established the kill requirements with scientific precision. 20 direct hits from 20mm cannons in critical areas, 30 hits if they were distributed across non-vital sections, a single 88mm flak hit to an engine nacelle, 2 or 3 13mm hits to the cockpit area. These weren't estimates. These were averages compiled from hundreds of after-action reports, gun camera footage, and wreckage analysis. But something was happening over Germany in early 1944 that was making a mockery of those calculations. B-17s were taking damage that should have been absolutely fatal, damage that exceeded every survivability threshold the Germans had documented, and still making it back to England. Not all of them, certainly. The 8th Air Force was still losing bombers at rates that would have broken any other air force, but enough were surviving the impossible that German fighter pilots were beginning to question their own tactics, their ammunition, even their sanity, when they watched fortresses they'd riddled with cannon fire continue flying in formation as if the laws of physics had been temporarily suspended. The phenomenon had started becoming noticeable to Luftwaffe intelligence in late 1943, but by February 1944, it was impossible to ignore. Mission after mission, German pilots were reporting the same impossible scenarios. They'd make perfect attack runs, observe their cannon shells exploding all over a B-17's fuselage and wings, count the hits in the dozens, sometimes hundreds, and watch the bomber keep flying, not limping, along at reduced altitude where it might be finished off, but maintaining formation at 20,000 feet, still capable of defending itself, still heading for its target. Major Heinz Noak, commanding officer of Jagdgeschwader 11, documented one such encounter on February 20th, just 3 days before Lawley's ordeal. His squadron intercepted a formation of B-17s over Brunswick and concentrated their attacks on a single fortress in the Low Squadron, the most vulnerable position in the combat box. Noak personally made 4 attack passes, expending all 660 rounds of his 20mm ammunition. His wingman, Lieutenant Werner Goeth, emptied his cannons as well. 2 other fighters from the Staffel joined the attack. In total, 4 Focke-Wulf 190 fighters poured approximately 2,420mm rounds at a single B-17 over the course of 12 minutes. Gun camera footage reviewed after the mission showed at least 140 confirmed hits on the bomber. The Fortress's tail section looked like Swiss cheese. Both horizontal stabilizers had gaping holes large enough for a man to crawl through. The rudder was missing entire sections of fabric and framework. The fuselage, from the waist windows to the tail wheel, was cratered with blast damage. Yet when the German fighters broke off, out of ammunition and low on fuel, that B-17 was still in formation, still flying level, still heading west toward England. Noakes' after-action report, preserved in Luftwaffe archives, contained a line that captured the growing frustration among German fighter pilots. The enemy bomber absorbed punishment that would have destroyed 3 of our own aircraft and continued flying as if protected by supernatural forces. What Noakes and his fellow pilots didn't fully understand was they were witnessing the convergence of 3 factors that had transformed the B-17 from a tough bomber into something approaching an airborne tank. First, Boeing and its subcontractors had made thousands of tiny improvements to the Fortress based on combat feedback from crews who'd survived the nightmare of 1943. Second, ground crews in England were implementing field modifications that went far beyond anything in the technical manuals. And third, the pilots flying these bombers had developed techniques for nursing damaged aircraft that weren't taught in any flight school because they violated every principle of safe aviation. The story of how B-17s started surviving damage that should have been absolutely fatal begins not in the boardrooms of Boeing or the Pentagon, but in the freezing mud of English airfields where 19-year-old mechanics were trying to keep their friends alive. Staff Sergeant Tommy Morrison of the 391st Bomb Group at Ridgewell had lost 3 crews he'd worked with in December 1943. All 3 planes had gone down from what Morrison considered preventable failures. Not from direct hits to engines or crew compartments, but from system failures that cascaded into catastrophe. Morrison, who'd grown up fixing tractors in Iowa farm country, had an insight that would have seemed obvious to any farm mechanic, but apparently hadn't occurred to Boeing engineers designing planes in climate-controlled Seattle offices. When you're 800 miles from the nearest parts depot and your tractor breaks during harvest, you don't follow the manual. You make it work with whatever you've got, and you build in redundancy because there's no such thing as too many backup systems when your livelihood depends on a machine not breaking. Starting in January 1944, Morrison began what he called farm-proofing every B-17 that came through his hangar. While official maintenance doctrine focused on keeping aircraft at factory specifications, Morrison was adding unauthorized backup systems, using parts cannibalized from bombers that hadn't made it back. He ran secondary hydraulic lines along different routes through the fuselage, figuring if flak took out one line, the backup might survive. He installed manual cable pulleys that could move control surfaces if the hydraulic boost failed. He reinforced critical wire bundles with armor plates stripped from written-off aircraft. He added drain holes in the fuel tanks so that even if the tanks were punctured, fuel wouldn't pool in the wings where one tracer could turn the whole aircraft into a torch. None of this was authorized. All of it added weight that reduced performance. And every modification took hours of work that Morrison and his crew did after their official shifts ended, working by flashlight in freezing hangars because they'd rather risk court-martial than watch another crew not come home from something preventable. Word spread among the maintenance crews across East Anglia. By February 1944, mechanics at dozens of airfields were implementing their own versions of Morrison's modifications. There was no standardization, no quality control, no official approval, just thousands of small changes that individually might save a system and collectively transformed the B-17 into something even tougher than Boeing had designed. But the mechanical modifications were only part of the equation. The pilots flying these bombers were developing their own techniques for surviving damage that should have been fatal. These weren't the green lieutenants fresh from flight school who'd filled the cockpits in 1943. By early 1944, the surviving pilots had 10, 15, sometimes 20 missions under their belts. They'd seen friends die, learned from their mistakes, and developed an almost supernatural ability to keep damaged aircraft flying. Captain Robert Morgan, pilot of the Memphis Belle and later chief of training for the 91st Bomb Group, had compiled what he called the survival manual nobody wants to write. It was a collection of techniques that worked but violated every principle of safe flying. Things like using the autopilot to hold a damaged plane steady while the pilot physically held broken control cables together, or deliberately flying in a slip to compensate for asymmetric drag when half your control surfaces were gone. Or the most controversial technique, keeping damaged engines running even when they were on fire, because the thrust might be the only thing keeping you airborne long enough to reach friendly territory. The manual was never officially published, but copies circulated among bomber crews like underground literature. Pilots would add their own notes in the margins, documenting tricks that had saved their lives. One annotation, found in a copy recovered from the 100th Bomb Group, described how to fly a B-17 with the entire tail section held on by just the control cables. Keep speed above 160. Any slower and the tail will fold. Ignore the vibration. If you can still feel it shaking, you're still alive. These pilots were pushing the B-17 into flight regimes that Boeing test pilots had never explored, because no sane test pilot would deliberately fly an aircraft with half its structure missing. But combat pilots didn't have the luxury of declaring an emergency and landing at the nearest field. Their nearest field might be 500 miles away across occupied Europe, and landing meant becoming a prisoner of war if you were lucky, or being lynched by German civilians if you weren't. Lieutenant William Lawley, fighting to keep cabin in the sky airborne on that February morning, was using every one of these unofficial techniques simultaneously. With his co-pilot dead and the intercom system destroyed, he couldn't communicate with his crew to know who was still alive. The bomber's autopilot had been shot out, so he was physically wrestling the controls every 5 seconds to keep the plane from entering a death spiral. The severed wing spar meant the wings were flexing independently, creating a Dutch roll motion that threatened to tear the aircraft apart. Lawley countered it by rapidly moving the ailerons in opposition to the roll, essentially flying 2 different control inputs simultaneously, one for each wing. The pursuing German fighters couldn't understand what they were seeing. Oberlieutenant Hans Wake of Jagdgeschwader 3 had made 6 passes at cabin in the sky, each time putting 20 to 30 rounds into the bomber. His flight leader, watching through binoculars from higher altitude, counted over 200 impacts on the fortress. Yet it kept flying, kept straight enough to maintain a westerly heading, kept together despite damage that should have caused immediate structural failure. What made the Germans particularly frustrated was that their ammunition was working exactly as designed. The 20mm mine shells, the Menengeschoss rounds that the Luftwaffe had perfected, were exploding on impact, each one blowing holes in the aluminum skin the size of dinner plates. The armor-piercing rounds were penetrating completely through the aircraft. The incendiary rounds were starting fires. Everything was working exactly as it should, except the bomber wouldn't fall. In his combat report, Wake wrote, "The enemy aircraft sustained damage incompatible with continued flight. Both outboard engines were destroyed or inoperative. The control surfaces showed numerous large holes. The fuselage was broken in multiple places. Yet it continued flying in defiance of all logic." The concept of survivable damage had been part of B-17 design philosophy from the beginning, but what was happening by early 1944 went far beyond anything Boeing engineers had imagined. The original B-17 design from 1935 had emphasized structural redundancy, multiple wing spars, so losing one wouldn't cause immediate failure. Multiple control cables, so a single hit wouldn't eliminate control. Multiple electrical buses, so system failures wouldn't cascade. But the modifications being made in the field had taken this redundancy to extremes that would have horrified Boeing engineers worried about weight and efficiency. Mechanics were installing backup systems for the backup systems. They were reinforcing structures that were already overbuilt. They were adding armor plate to areas that statistical analysis showed were rarely hit, just in case. Master Sergeant James Chen at Thorpe Abbotts had taken this to perhaps its greatest extreme. He'd analysed the loss reports for every B-17 in the 100th Bomb Group and identified what he called cascade failure points, single locations, where damage could trigger a series of failures that would bring down the aircraft: the main hydraulic distribution junction under the radio room floor, the electrical bus bar behind the pilot's seat, the oxygen manifold in the bomb bay. Chen's solution was elegant in its brutality. He surrounded each of these points with armor plates scavenged from tanks that had been shipped to England for the eventual invasion of Europe. The tank crews didn't need belly armor while training in England, and Chen figured the bomber crews needed it more while flying over Germany. By February 1944, every B-17 Chen touched had nearly 300 pounds of extra armor that wasn't on any weight and balance chart. The extra weight should have reduced performance significantly, and it did. But it also meant that bombers were surviving direct flak hits to previously vulnerable areas. A Fortress from the 100th took an 88mm hit directly under the radio room on February 15th. The explosion should have destroyed the hydraulic system, electrical system, and control cables simultaneously. Instead, Chen's armor plate absorbed most of the blast. The plane lost some systems but maintained enough control to limp home on 2 engines. But armor and redundancy only explained part of the survival phenomenon. The third factor, and perhaps the most important, was the revolutionary change in how damaged bombers were being flown. The standard procedure taught in flight school was to reduce weight and drag when an aircraft was damaged, jettison the bombs, throw out any unnecessary equipment, reduce speed to best glide, and try to maintain altitude as long as possible. Combat veterans had learned this was exactly backward for a damaged B-17. Captain John Lucky Egan of the 100th Bomb Group had survived, bringing back B-17s that looked more like colanders than aircraft, and he'd developed what he called the power-through philosophy. When your bomber took catastrophic damage, you didn't reduce power to save the engines. You pushed everything to maximum, even if the engines were burning, even if the cylinder head temperatures went off the scale, even if every gauge was redlined. The reasoning was brutally simple. You could either nurse your dying engines and possibly extend their life by 20 minutes before they failed completely, leaving you over occupied Europe. Or you could run them at full power, get maybe 10 minutes before they seized, but cover twice the distance in that time. Every mile toward England increased your chances of survival exponentially. Every minute at maximum power might be the difference between reaching the Channel or ending up in a German field. Part 2. This philosophy extended to every system on the aircraft. Hydraulics, losing pressure, don't conserve it by limiting control movements. Use maximum deflection while you still can to get the plane pointed toward home. Electrical system failing? Don't shed load to preserve battery power. Use everything while it works to navigate and communicate your position. Fuel leaking from punctured tanks? Don't reduce power to conserve fuel. Burn it before it drains out and use the thrust while you have it. This approach horrified Boeing engineers when they learned about it after the war. They designed safety margins into every system, expecting pilots to respect those limits. Instead, combat crews were deliberately exceeding every limitation, pushing engines until they literally melted, flying with control surfaces that were barely attached, maintaining flight with structures so damaged that post-flight analysis couldn't explain how they'd held together. Lieutenant Colonel Robert Rosenthal, commanding officer of the 418th Squadron, had perhaps the most extraordinary example of this philosophy in action. On February 8, 1944, his B-17 took over 200 hits during a running battle with German fighters over Berlin. The damage was so extensive that when he landed at an emergency field in England, the engineering officer took one look at the aircraft and declared it impossible that it had flown in that condition. The entire rear fuselage was separated from the front, held together only by control cables and a thin strip of skin along the belly. Both horizontal stabilizers were missing more than half their surface area. The rudder was gone entirely except for the spar. All 4 engines showed evidence of fires that had been somehow extinguished. The fuel tanks had over 40 holes, patched from inside the aircraft during flight by crew members, using chewing gum and canvas strips cut from parachutes. When asked how he'd kept such a destroyed aircraft flying, Rosenthal's answer was simple. You don't fly it. You will it to stay in the air through pure determination. The Germans studying these impossible survivals were reaching disturbing conclusions about their own tactics and weapons. The Luftwaffe's fighter doctrine had been built around achieving quick, clean kills through concentrated firepower. The standard armament of 4 20mm cannons and 2 13mm machine guns on a Focke-Wulf 190 was supposed to be more than sufficient to destroy any bomber with a well-placed burst. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But the B-17s of early 1944 were proving nearly impossible to kill cleanly. The combination of official improvements, unauthorized field modifications, and revolutionary flying techniques had created something unprecedented in aerial warfare. A bomber that could absorb damage equivalent to its own empty weight in enemy ammunition and keep flying. German ace Major Wilhelm Reschke conducted an informal study of his squadron's combat reports from January and February 1944. He calculated that on average, his pilots were expending 800 rounds of 20mm ammunition per B-17 claimed destroyed. At earlier stages of the war, that number had been closer to 200 rounds. The ammunition expenditure had quadrupled while the actual number of bombers destroyed had decreased. Even more troubling for the Luftwaffe was the discovery that many B-17s they thought they'd destroyed were actually making it home. German intelligence had been counting bombers that left formation trailing smoke or with obvious severe damage as confirmed kills. But reconnaissance flights over English airfields were revealing some of these same aircraft, identified by squadron markings and tail numbers, back in service weeks later. The repair capabilities of American maintenance crews were matching the survival capabilities of the aircraft themselves. B-17s were landing with damage that would have scrapped any other aircraft, and within weeks, sometimes days, they were flying again. The 303rd Bomb Group at Molesworth had a fortress called Patches that had been shot down 3 times, each time making forced landings in England, each time being rebuilt from salvaged parts and returning to combat. Master Sergeant Tony Stasser, crew chief for Patches, had essentially built a new airplane around the original data plate. By February 1944, the only original parts were some of the cockpit framework and the pilot's control column. Everything else had been replaced, sometimes multiple times, using parts from 17 different written-off B-17s. The plane flew with mismatched engines from different production blocks, wings from 2 different aircraft, and a tail section that had been transplanted wholesale from a bomber that had burned on the runway. This ability to resurrect seemingly destroyed aircraft was multiplying American combat power in ways German intelligence hadn't anticipated. They were calculating American losses based on aircraft destroyed, but many of those destroyed bombers were returning to service. A B-17 that survived, no matter how badly damaged, could be rebuilt. A B-17 that went down in Germany was gone forever. The psychological impact on both sides was profound. American crews were developing an almost mystical faith in the B-17's ability to get them home. Stories of impossible survivals spread through the bomber groups like mythology. Lawley's flight in Cabin in the Sky would become legendary, adding to a growing collection of tales that gave crews hope even when facing horrific losses. Conversely, German fighter pilots were beginning to experience a crisis of confidence. They were doing everything right, executing perfect attacks, achieving numerous hits, expending all their ammunition, and watching bombers continue flying. It was demoralizing to risk your life making attack runs through defensive fire, achieve what should be a kill, and see your target still heading for England. Lieutenant Hans-Georg Becher of WWII described the frustration in a letter to his wife. "We hit them again and again, see our shells exploding all over their aircraft, and they keep flying as if protected by guardian angels. Sometimes I wonder if our ammunition is defective, but then I remember we're using the same shells that worked perfectly well last year." What Becher and his fellow pilots didn't fully appreciate was that they were now fighting a different enemy than they'd faced in 1943. The B-17 hadn't just evolved, it had been transformed through a combination of official improvements, unofficial modifications, and revolutionary tactics into something that transcended its original design. The official improvements from Boeing were significant but evolutionary. Stronger wing spars, better self-sealing fuel tanks, improved armor around crew positions, Tokyo tanks in the wings that could be filled with fuel or left empty depending on mission requirements, Strengthened tail sections after analysis showed this was a vulnerable area. Better oxygen systems with backup regulators. Improved heating for guns to prevent freezing at altitude. Each improvement by itself was marginal, perhaps increasing survivability by 1 or 2%. But cumulatively, they were significant. A B-17G model from early 1944 was roughly 15% more survivable than an F model from early 1943, according to post-war analysis. That meant for every 100 aircraft that would have been lost in 1943, 15 were now surviving. But the unauthorized field modifications were having an even greater impact, though one that was harder to quantify because they were never standardized or officially documented. Every bomb group had its own variations, its own mechanics with their own ideas about what would keep their planes flying. Some focused on hydraulic redundancy, others on electrical backup systems, still others on structural reinforcement. The 381st Bomb Group at Ridgewell had a mechanic who'd worked in a steel mill before the war. He was heat-treating critical structural components to increase their strength, using improvised furnaces made from oil drums and aviation fuel. The treatment made the aluminum alloy more brittle but significantly stronger, able to withstand impacts that would shear untreated metal. The 91st Bomb Group at Bassingbourn had developed a system of cable stays that could be rapidly installed if the main wing spar was damaged. Crews carried special clamps and pre-cut cables that could essentially create an external skeleton for the wing, transferring loads around damaged sections. It was ugly, induced massive drag, and made the plane nearly unflyable. But it kept wings attached long enough to get home. The 445th Bomb Group at Tibenham took a different approach, focusing on damage control during flight. They trained their crews not just to operate guns and drop bombs, but to conduct emergency repairs while under fire. Gunners learned to patch fuel tanks using special rubber sheets and adhesive that would bond even at -40 degrees. Radio operators knew how to splice control cables. Navigators could reroute hydraulic lines. These crews carried toolkits that would have amazed Boeing engineers. Bolt cutters to remove damaged sections of structure, pop rivet guns to install patches, rolls of high-strength wire for emergency repairs, even small welding torches, though using them in a bomb-laden aircraft full of fuel vapor required either incredible bravery or complete insanity, possibly both. The tale of Lieutenant David Kingsley's crew illustrated this evolution in dramatic fashion. On February 11, 1944, their B-17 was attacked by an estimated 15 to 20 German fighters over France. The bomber took catastrophic damage. The tail gunner was killed instantly. The ball turret was jammed with the gunner trapped inside. Both waist gunners were wounded. The radio operator was unconscious from lack of oxygen when his mask was severed, but instead of abandoning the aircraft, the surviving crew went to work. The navigator crawled back through the fuselage, dodging incoming fire, to free the ball turret gunner using a crowbar to pry open the jammed mechanism. The bombardier patched fuel leaks using canvas cut from a parachute and adhesive that froze solid in the sub-zero air, creating improvised seals. The flight engineer manually pumped hydraulic fluid from a reserve tank, maintaining just enough pressure for basic control while cannon shells continued to punch through the fuselage around him. The pilot and co-pilot flew the aircraft using a technique they'd learned from combat veterans, one handling the control column, the other physically pulling on the elevator cables that ran through the cockpit, adding direct mechanical input when the hydraulic boost failed. They made it to the channel before the last engine died, ditching successfully close enough to the English coast that rescue boats reached them in minutes. The German pilots who'd attacked them filed reports claiming certain destruction of the bomber. They'd observed over 150 hits and seen 2 engines completely destroyed. By their calculations, the aircraft couldn't possibly have survived. Yet most of the crew did survive, rescued from the channel, flying again within weeks in another fortress. This pattern repeated across hundreds of missions. German pilots claiming kills that weren't quite kills. American bombers surviving damage that shouldn't be survivable. Each mission adding to the cumulative experience that made the next survival slightly more likely. What made William Lawley's flight in Cabin in the Sky particularly remarkable wasn't just the extent of the damage, but how he used every trick in the evolving survival playbook. When the explosion killed his co-pilot and damaged the control columns, Lawley didn't just try to fly with reduced control authority. He used his belt to lash the co-pilot's body to the control column, using the dead man's weight to help hold the elevator in position while Lawley handled the ailerons and rudder. When the intercom failed, cutting communication with his crew, Lawley established a system of signals using the engine throttles, advancing and retarding them in patterns the engineer could see on his gauges, creating a crude but effective communication method that allowed coordination of emergency procedures. When fuel began leaking from multiple tank punctures, the engineer didn't just try to transfer fuel from damaged tanks. He climbed outside onto the wing at 20,000 feet without a parachute because the weight would have prevented him from moving, and manually held a transfer valve open while fuel sprayed over him in the 200-mile-per-hour slipstream. He nearly froze to death, his hands becoming blocks of ice gripping the valve, but he transferred enough fuel to the inboard engines to keep them running. The bomber's survival seemed to mock physics. The severed wing spars should have caused immediate catastrophic failure. The destroyed control systems should have made controlled flight impossible. The fuel leaks should have drained the tanks in minutes. The structural damage was so extensive that when Cabin in the Sky finally landed at an emergency field in England, it broke in half on the runway, the fuselage separating completely just behind the wing. The fact that this catastrophic failure waited until the aircraft was safely on the ground seemed like divine intervention. The engineering report on Cabin in the Sky, filed weeks later after extensive analysis, contained a remarkable admission. The aircraft's survival cannot be explained by conventional structural analysis. The combination of damages should have resulted in immediate catastrophic failure. The fact that controlled flight was maintained for over 2 hours suggests either our understanding of structural mechanics is incomplete or other factors beyond pure engineering were involved. Those other factors were the intangibles that couldn't be measured or calculated. The determination of pilots who refused to give up, the skill of mechanics who built in safeguards that weren't in any manual, the courage of crew members who conducted impossible repairs while under fire, the accumulated knowledge of hundreds of crews who'd learned what worked and passed it on. By March 1944, the Luftwaffe was forced to acknowledge that their existing tactics and weapons were insufficient against the evolved B-17. Reports from fighter groups were consistent. The bombers were simply too tough to kill with conventional attacks. New solutions were needed, and they were increasingly desperate. The introduction of the 30mm Mk108 cannon was one response. This massive weapon fired shells nearly twice as heavy as the 20mm rounds, with devastating explosive power. A single 30mm hit could tear off a wing or destroy an entire engine nacelle. But the weapon had drawbacks. Its low muzzle velocity meant fighters had to get very close to ensure hits, well within the range of defensive .50 caliber fire. Some fighter units experimented with aerial ramming, the deliberate collision with bombers as a last resort. Major Heinrich Oehler of Jagdgeschwader. 5 documented procedures for survivable ramming attacks, aiming to clip the bomber's tail with the fighter's reinforced wing, hoping the fighter pilot could bail out after the collision. It was a tactic of desperation, trading a fighter and risking a pilot to ensure destruction of a single bomber. The development of the Sturmbok units represented another evolution. These were Focke-Wulf 190 fighters with additional armor plate, designed to bore through defensive fire and attack at point-blank range with heavy cannon. The extra armor made them slow and unmaneuverable, vulnerable to escort fighters, but they could absorb hits from .50 caliber guns long enough to press home attacks. Yet even these desperate measures couldn't overcome the fundamental equation. The B-17s kept coming, kept surviving, kept dropping their bombs. Each mission that returned, no matter how damaged, represented a victory for the American strategic bombing campaign. Each survival story reinforced the belief among American crews that their fortresses would get them home. The Germans, studying the wreckage of bombers that didn't make it back and intelligence reports on those that did, were reaching an uncomfortable conclusion. They were witnessing the convergence of superior engineering, innovative field modification, revolutionary tactics, and human determination that had created something unprecedented in aerial warfare, a.d., a bomber that could absorb damage beyond all reasonable limits and keep flying. Major General Adolf Galland, commander of German fighter forces, would later write, "The B-17's survivability by 1944 had exceeded our ability to destroy them in sufficient numbers. We could damage them, riddle them with holes, set them on fire, destroy their engines, and still watch them disappear toward England. It was militarily and psychologically devastating." The truth was that the B-17 had evolved far beyond its original design, through a process that no single organization had controlled or planned. Boeing provided the foundation. Official improvements added incremental advantages. Field modifications multiplied redundancy. Revolutionary flying techniques pushed the aircraft beyond designed limits. And human courage tied it all together. Each B-17 that survived impossible damage became a lesson for others. Each crew that made it home, despite catastrophic battle damage, added their knowledge to the collective experience. Each mechanic who invented a new modification shared it with others. The result was an aircraft that by early 1944 had transcended its mechanical nature to become something almost mythical in its ability to survive. William Lawley received the Medal of Honor for his flight in Cabin in the Sky. The citation noted his determination and skill in bringing his crippled bomber home, but those words couldn't capture the full reality of what had happened. He'd flown an aircraft that shouldn't have been flyable, using techniques that shouldn't have worked, surviving damage that shouldn't have been survivable. The 217 20mm hits that Cabin in the Sky absorbed would have destroyed any other aircraft in existence. The fact that it flew for nearly 3 hours in that condition, covered 500 miles, and delivered its crew home safely represented the culmination of everything that had evolved in the B-17 program. It was proof that the Flying Fortress had become something more than the sum of its parts. The German pilots, who witnessed these impossible survivals, were left with a mixture of frustration and reluctant admiration. They'd done everything right, executed perfect attacks, achieved numerous hits, and still failed to bring down their targets. It wasn't a failure of skill or courage on their part. They were simply fighting against something that had evolved beyond their ability to destroy it with conventional means. By the spring of 1944, the sight of heavily damaged B-17s limping back to England had become routine, bombers landing with entire sections of fuselage missing, aircraft touching down on one wheel with the other gear leg shot away, fortresses returning with dead engines, dead crew members, and damage that defied belief. Yet they returned, again and again, carrying their crews home and preparing to fly again. The evolution would continue through the rest of the war. More improvements, more modifications, more accumulated knowledge. By 1945, B-17s were surviving damage that would have seemed like fantasy in 1943. The aircraft that had started the war as a tough bomber had evolved into something approaching indestructible, at least by the standards of World War II aerial combat. The legacy of this evolution extended far beyond the war itself. The lessons learned from B-17 survivability influenced aircraft design for decades. The importance of redundancy, the value of field feedback, the critical nature of damage control procedures, and most importantly, the recognition that aircraft survivability wasn't just about engineering, but about the complete system of aircraft, modifications, tactics, and human factors. The B-17 Flying Fortress earned its legendary reputation not through any single factor, but through the convergence of multiple evolutionary pressures that transformed it from a good bomber into an extraordinary survivor. By early 1944, it had become exactly what its crews needed it to be, a machine that would get them home no matter what the enemy threw at them. The 200-plus cannon hits that some B-17s survived represented the extreme edge of this capability. But they proved something important. With enough redundancy, enough determination, and enough accumulated knowledge, even the impossible became possible. The Luftwaffe never expected B-17s to survive such damage, because by all conventional analysis, they couldn't. The fact that they did anyway changed the course of the air war over Europe and proved that sometimes reality exceeds what any calculation would predict. The young men who flew these battered fortresses home who patched them in freezing hangars, who figured out how to make them survive the unsurvivable, had created something unique in the history of warfare. They'd taken a machine designed by engineers and transformed it through practical experience into something that transcended its original limitations. The B-17 Flying Fortress of 1944 wasn't just built in factories. It was rebuilt in combat, one impossible survival at a time. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now.